In this video, we're going to start looking at our bonding summary. I think this is one of the most important double-page spreads that we look at in our chemistry lessons. It's a summary of probably what is nearly a term's work, looking at the three types of chemical bonding. So the three types of chemical bonding are ionic, covalent, and the third one over here is metallic. We're not going to go through all of them in this video because it will simply be too long. But over a series of a couple of videos, we'll build up the ionic, covalent, and metallic descriptions. First off then, bonding. Why do atoms bond together? Atoms bond together to get a full outer shell of electrons. And we have to write that down before we go any further at all. So I'm going to put it at the top here, and we'll probably put a few things around the side as this goes on. So atoms bond together to get a full outer shell of electrons. Now, just to explain this a little bit further, if we look at the periodic table, we can see it's comprised of about 100 different elements. What that means is everything in the universe is made up of those 100 different elements. Now, you just look around the room you're sat in right now. There's probably thousands of different materials there, and that's the fantastic and fabulous thing about chemistry, really, is that that all those things are made from just those 100 or so different elements, and that happens because they join together in different ways to make different substances. And that's what chemistry is. It's about learning how they join together to make these different substances. And there's three ways they can join together. They can join together ionically, covalently, or metallically. And they do. And the reason they do this is because the atoms themselves want a full outer shell of electrons. Right. First up in bonding, ionic. A description of an ionic bond. Well, an ionic bond involves metals, and non-metals. So that's the first thing we can say to this. If you identify the type of elements that make up a compound, we can immediately say what type of bonding is present by the atoms that are involved. Now, if you're not sure whether something's a metal or a non-metal, have a quick look on the periodic table. The periodic table tells you everything, of course. So the periodic table looks a little bit like this. Let's quickly sketch out a periodic table over here. Let's do this group here. This group has 6 groups in it. There they are. 1, 2, 3, 4, 5, 6. Yes, and there we go. That many rows. So the metals are found on the left-hand side of the periodic table, and there is an invisible stepwise line that goes down there like that. There we go. And the metals are found on this side. So the metals are found on this side. The non-metals are on this side. So if an element is found here, that will be chlorine, for example, and over here we could have sodium in this group. We can see there's one on the metal side and one on the non-metal side, so that would be an ionic bond. Okay, something from a metal side and a non-metal side makes an ionic bond. Now what happens is the metal gives an electron or electrons to the non-metal. Okay, metals are found on the left-hand side of the periodic table. So they have, in this case, in group 1, 1 electron in its outer shell, or group 2, 2 electrons in its outer shell. Group 3, 3 electrons in the outer shell. So they've got a few electrons in their outer shell. So they've always got a choice. Okay, when they want to get a full outer shell, they can either gain electrons or lose electrons. Okay, so the metals only have a few electrons, so they lose them. The non-metals on the right-hand side of the periodic table, their electron shells are almost full. So the halogen group here, group 7, they've got 7 electrons in their outer shell, or they need 1 more if you like, so they will gain electrons. So the metal always gives an electron to the non-metal. In passing that electron over, the atoms become charged. This gives us positive metal ions. Next thing for the top here, an ion. Should we write it over here? I'll do it on the side. An ion, definition of an ion. a charged atom. A charged atom. So when those metals and non-metals give or take electrons, they become charged. And when they become charged, we don't call them atoms anymore, we call them ions. An ion is a charged atom. This gives us positive metal ions and negative non-metal ions. And the last thing to say is the oppositely charged ions attract each other. The opposite charges, I'll put the opposite charged ions attract. So actually, I know it's cool, we've got it under an ionic bond, but actually it's an ionic attraction. An ionic attraction. Right, an example. Let's put a couple of examples down here. So we could have an example with sodium 11 and chlorine 17. I've written the atomic numbers down there. If we look on the periodic table, you can always find the atomic numbers. Let's put those there. Let's also put magnesium 12 here and oxygen 8. So we'll do 2 examples. Okay, first one, sodium 11. Dot for the nucleus to start with, and 2 electrons on the first shell. So there's 11 electrons in total. The atomic number tells us that. Let's make these crosses a little bit clearer. 2 electrons on the first shell, 8 on the second. 2 and 8 makes 10 electrons. Okay, so that's 8, there's 10. I've got 11 electrons in total, so 1 electron on the outer shell. So we can immediately look at that and say, this is going to want to get a full outer shell of electrons, either by gaining 7 electrons to fill this outer shell, or it's going to lose that 1 electron. If it loses an electron, this shell ceases to exist. Okay, so we sometimes call these shells orbitals, and like in the same way the Earth orbits the Sun. If the Earth didn't exist, there would be no orbit. If that electron goes, there is no shell, there is no orbit. So the shell underneath is full, and that shell would become the outer shell. Chlorine over here, 17 electrons. 2 on the first shell, 8 on the second, 8 on the second, and there's 2 on the first to make 10, which means there's 7 electrons on the third shell, because the third shell will hold 8 in total as well. So this has got 7, so it can either lose 7 or gain 1. Now the secret is it always does whichever's least. So that electron there is going to go to there. Now we're going to draw the arrow. I'm going to show this electron moving with an arrow. We're going to draw the arrow starting at the electron and finishing at the gap. And we will label that E minus transfer. E minus is a nice abbreviation for an electron. And what you can see is that negative charge is going over to the chlorine. So the question at the end of this is which of these is positively charged and which of these is negatively charged. So if you've drawn the negative charge going this way, hopefully you can see that the chlorine is negative. Look, that negative is going towards the chlorine. This is the chlorine, the chloride ion. So we write Cl minus there. If that's negatively charged, this one has to be positively charged. And there's that age-old joke in chemistry, isn't there? 2 atoms walking down the street. One says to the other, I think I've lost an electron. And the first one says, are you positive? Hopefully you get it. Lost an electron, are you positive? Lost an electron, positive. Lost the electron, positive. Okay, enough of that. Plenty of examples of ionic bonding. If you want more examples, there's more examples in the front of your book. Okay, but this is just another example here. Magnesium, 12 electrons, 2 on the first shell, 8 on the second. 2 and 8 makes 10, and that's going to make 2 electrons in the outer shell. So this time we've got 2 electrons in the outer shell, so it's going to want to lose 2 or gain 6. Same as before, it does whatever is least. Oxygen, 8 electrons in total. 2 on the first shell and 6 on the second, like so. So hopefully we can see now this is going to want to gain 2 electrons, this is going to want to lose 2 electrons. They can go over there. Let's draw an arrow starting electron, finishing at the gap. Arrow starting electron, finishing at the gap. Now I say label every arrow E minus transfer because it says to the reader, I know what I'm talking about. I know that electron, this magnesium shifts 2 electrons to the oxygen because I've written it twice. So 2 negatives go into the oxygen, so that's going to be O2 minus. Okay, because it's gaining 1 electron, 2 electrons, O2 electrons, 2 minus if you like. Magnesium, losing 2 electrons, so that's going to be Mg2 plus, 2 plus, like so. Right, the formula of both of these, Quite easy, and maybe I've picked examples that are a bit similar in this case. But to do the formula, we need to count the number of ions. Some students count the number of electrons. Don't do that. Don't do that. We're counting the number of ions. So how many ions do we have in this example? How many sodium ions do we have in this example? We've got 1 sodium ion. So the formula is going to be Na1. We never bother writing the 1 because I wrote the Na. I've got 1 chloride ion, so that's going to be NaCl. And that's the formula. There's one of both. Different ionic examples can have different number of ions, so we can have different numbers underneath. 1 magnesium, 1 oxygen here, exactly the same, so the formula is MgO. And the names of both of these, this one is going to be called sodium chloride. We always put the metal name first. Sodium is the metal because it's on the left-hand side of the periodic table. Sodium's over here on the periodic table. And the non-metal goes second. Now, the non-metal changes its name when it bonds. That's how we know it's a compound. And the ending "ide" means only. So this is what this means is a compound of sodium and chlorine only. This one over here, magnesium oxide, because it's magnesium and oxygen only. Some compounds have for example, like copper sulfate is CuSO4. So that's made of 3 different atoms, if you like. So the name of this one is not going to be copper sulfide. CuS, that would be copper sulfide because that's copper and sulfur only. When you have copper, sulfur and oxygen, we change this ending "ide" to 8. So that would be copper sulfate. Right, structure. So the structure of all ionic compounds is an ionic lattice. One of my favourite facts in chemistry is that you can fit 4 billion sodium atoms on a full stop. Okay, so atoms and ions are tiny. So we've drawn sodium chloride here. We've drawn 1 sodium atom that became an ion and 1 chlorine atom that became a chloride ion. Even if we've got the smallest grain of salt imaginable, there's going to be thousands of millions of ions present. So we can't just think about 1 atom when we're thinking about the structure of a grain of salt. So what we need to do is we need to think about lots of ions and how they all interact together. So that positive ion there, I've just drawn, could be that positive ion there. And this negative ion here could be that negative ion there. Okay, so that positive ion gave its electron to that chloride ion. Now, just as that's happened with those two, there's going to be plenty of others. So there might be another positive ion here, and this may have given it its electron to this chloride ion there. Okay, and they attract because oppositely charged ions attract. But as well as that ion attracting that ion is going to attract that ion. In fact, all positive ions are going to attract all negative ions. So there'll be another negative ion there, another positive ion here. And what we're going to get is a structure of alternating positives and negatives. And this will be a regular arrangement. Regular means neat and tidy. Okay? Now, I often joke with the classes I teach that they need to go and their homework for tonight at the end of the lesson, they need to go and they need to go to the local fish and chip shop. It's Gotterson's in Aylsham. And they need to ask for a bag of chips, and that's their homework, and their parents need to get them this bag of chips. But they can only have it so long as they ask for some sodium chloride on the chips at the end of it. Sodium chloride is, of course, common salt. So that's what we've got here, a structure of common salt. And I want them to look at the sodium chloride crystals that are tipped onto the chips. And I want them to look at the cuboid shape, because this arrangement of positive and negative ions will make an absolutely beautiful cube. Okay, and they need to say to the chip shop owner, look at that beautiful ionic lattice. Okay, they're small crystals, but they are cuboid in shape, and it's sometimes quite nice to be able to draw that. And all ionic substances have a lattice that is similar. They can be different shapes because sometimes there's different formulas to these compounds. So copper sulfate, we looked at a moment ago, they have diamond-shaped crystals. But salt crystals, sodium chloride crystals are cuboid because you have this regular arrangement of oppositely charged ions attracting each other. And between these, there are strong forces of attraction. Okay, those positive ions attract those negative ions strongly, which means the melting point must be high. High melting point. Because of strong forces of attraction. Strong forces of attraction. between oppositely charged ions.